going to apply this to a couple of actual examples. Let me blow this up a little bit so I can see it a little bit better. The mean of a population is known to be 160. The standard deviation of the population is known to be 20. So we know the mean and the standard deviation of the population. What would the probability that a single observation selected at random from the population would have a value of less than 154? Well, how would I do that? I'm just dealing with a normal distribution and a population. So I'd use the Z table for that, right? So I would look up X minus mu, 154 minus 160 would be 6, divided by the standard deviation, which is 20. So 6 divided by 20, hang on, what's that? Minus 6 divided by, good, minus 6 divided by 20 is 0.0, what is it, 0.3? Negative 0.3? No, negative point, let's see, 6 out of 20 is, it's 15, right? 0.15, yeah. Negative 0.15, am I right there? Yeah, negative 0.2, no. 0. No, that would be, right, you're negative 0.3. Okay, good. That took long enough to figure out. Negative 0.13. So negative 0.13, 0.13 would represent, it looks like 44.448. Am I right there? Is 44.8% of the population would be between that, below that value. So at any rate, I'll find a lozenge here. So.
I thought the Z value is -0.3.
Oh, it was a negative point. Did I ignore you and just say my own, came up with my own value? Yeah, 0.3 would have been 38%, approximately 38% would be below 54, right? So this is something we've been doing all along, repeatedly. We're looking at the Z table to get to judge the distribution of the population and to decide what the probability of getting a specific outcome for an individual chosen at random would be. So now I'm going to go back and look at this again. And I'm starting to think Levi should have stayed home, should have come in, I should have stayed home. Okay, so a single probability, a single observation is a value greater than 166. We do the same thing. We calculate the Z-score, look at the area, just as we've done before. Okay, now we're going to change this a little bit. Let's say instead of dealing with a known population, you take a random sample of size n, and that sample has a mean of 150. We're going to assume that the population is normally distributed with a standard deviation of 30, sigma equals 30. So we know the mean of our sample, and we know the standard deviation of the population. Calculate the standard error for samples of size 100. Now, the standard error is the distribution of sample means from this population of size 100. Okay, so let's take a look at that. What would that be equal to? That's going to be equal to sigma over the square root of the sample size. Sigma is 30. The sample size is 100. The square root of 100 is 10. So it's 30 over 10 would be 3. So the standard error is equal to 3. So the distribution, the standard error, the standard deviation for repeated samples of size 100 for this population is going to be 3. Because we know this, we can say this because we know the population standard deviation. Okay, how about let's see, compute a 95% confidence interval for the mean of this population. Okay, we don't know the population, do we? So I'm going to pull this sheet up and I'm going to work this out here. Okay, so what did we know? We knew that n is equal to 100. Our sample mean was equal to, what was it equal to? 50? 150? Okay. And sigma for the population was equal to 30. So our standard error is equal to 30 divided by the square root of 100, right? That's sigma over the square root of n. Okay, it's going to be equal to 3. Okay, so now we want to build our confidence interval. So our confidence interval is equal to the mean plus or minus our margin of error, which is equal to some value for z. That value for z depends on what our confidence interval is, right? Times the standard error. So let's do this for a 95% confidence interval. For a 95% confidence interval, we know the population standard deviation, so we're going to use the value 1.96 to represent 95% of the possible values. So that's going to be equal to 150 plus or minus z, which is 1.96, times 3. Now I'm going to take the liberty of calling this 2 for the moment, right? So we get plus or minus 6. So our confidence interval is going to be 149 on the lower end and 156 on the higher end. Okay, so we're 95% sure the true mean for this population is between 149 and 156. Do we know what the mean is? No, we don't know the population mean. We just know a range for the population mean. Is it more likely to be 149 than it is to be 155 or 150? We're really not speculating with that. All we're doing is saying that our point estimate, our most likely view of what the mean is 150 because that's what our sample says. But we can say with 95% confidence, it's between 149 and 156. Not 100% confidence, 95% confidence. Well, what if I want to be more confident? Yes. The 140, I'm sorry, 139. 130. Am I right? Right. Excuse me. 144. Yep. I subtracted 6 from the 150. Okay, catch me when I do that, okay? So I can correct it right away. So it's 144 to 156. Now, 99% confidence, I want to be more confident that I've captured the mean this time. So I want my confidence interval to be wider. Well, I don't even really think about that because for my 99% confidence interval, I know to capture 99% of the possible outcomes if they're normally distributed, I would need to use a z-score of 2.58 instead of 1.96. How do I know that? Well, I looked it up in the table before, the z-table. So now instead of 1.96, I would be using 2.58. So it would be 150 plus or minus 2.58 times the standard error, which is 3. Okay, and again, I'm going to take the liberty of calling this 2.5, 7.5. So I'd subtract 7.5 from 150, and it would be approximately 142.5 and 157.5. Okay, it's a wider interval than 144 to 156. Did I have to really think about it? No, that using that 2.58 took care of that for me. How about a 90% confidence interval? What am I going to use for that? 1.64, right? And you can actually go through the math and it'll come out to be a narrower confidence interval. You can have a narrower confidence interval because you're willing to be less certain that you've really captured the mean. Okay, so let's take a look at the next example. Okay, let me just make sure you guys online are doing okay. Are you with us online there? Are you guys doing okay? Okay. Oh, yeah, look at that. I've been getting some actual answers, and they're using their calculators. Good, thank you. Okay, so let me cancel that. Okay, let me go back to my document here. Okay, calculate standard error. Let's see, next one here. Random sample of size 36 has a mean of 150, very similar to what we had before. Assume the population is normally distributed with a standard deviation that equals to 30. Okay, so now calculate standard deviation, standard error for a sample size of 36. See any problems with this? Right? I do it exactly the same way. Do I care about the sample size? Probably not. Why do I not care about the sample size? Because what do I know here? I know the population standard deviation, and I'm assuming that the population is normally distributed. If the population is not normally distributed, then there's a problem. But if we know the population standard deviation is normally distributed, it doesn't matter really what the sample size is. Sample size really impacts us when we start to talk about not knowing the population standard deviation. Okay, so in this case, the standard error is going to be equal to sigma, which is 30, over the square root of the sample size, which is 36, would be 30 over 6. So the standard deviation, standard error here would be equal to 5 instead of 3. So our confidence interval is going to be 150 plus or minus 1.96 times 5, right, instead of times 3. And you just do the same calculation.